Okay, this is another video in the series for Math 1224 for UTSA. Today, we're going to be talking about the method of partial fractions. To start with, we're going to review a few concepts that we already have, particularly from Cal 1, really. And then we'll look at how to leverage them to work other kinds of problems. And while we're doing that, we will have to review some algebra that you may not have seen in a while. So let's get started. So this first example, we have an integral here, an antiderivative. And you might notice that the numerator is proportional to the derivative of the denominator, right? If you find the derivative of the bottom, you'll get 2x plus 4. And if you were to double the top, that would be the same thing. So that means we get to do a relatively simple substitution. We can say, oh, well, u equals x squared plus 4x plus 5. So du equals 2x plus 4 dx, right? So if I borrow a 2, basically, put a 1/2 out front, and then pair the 2 and the x plus 2 with the dx, I can get this. 1 over x squared plus 4x plus 5, right, times 2 times x plus 2 times dx. So when I go to do my substitution, I get 1/2 integral of 1 over u du, and this is a relatively easy integral at this point. I get ln, well, 1/2 times ln of the absolute value of u, plus c, of course, and then I can plug u back in, and I get 1/2 ln of the absolute value of x squared plus 4x plus 5 plus c. And potentially, not in this case, I don't think, but potentially, I didn't check, but maybe this argument is always positive anyway. So in some cases, we can even drop the absolute value bars. So for some rational functions, you just need a substitution. If you're lucky, this kind of substitution will work. Sometimes it won't, sometimes it will. What about the next example? For this one, all I did was change the numerator to just be 1. So that substitution will not work here because the derivative of the bottom is not a multiple of the top, right? So what we need to do with this one is something else. We're going to need to use some algebra because I know that if we're able to get it to look like the integral of 1 over 1 plus u squared, let's write that a little bit better, 1 plus u squared du, well, then this is just tangent inverse of u. That's relatively easy once we get in that format. So I need to basically complete the square on this quadratic. And this may be something you haven't done in a while, so of course we'll review how to do that. So if I have x, let's do it over here. If I have x squared plus 4x plus 5. In fact, I'm going to run out of room if I do that, so let's do this. Yeah, that's fine. That's fine. What I want to do is the 5 is just sort of a buffer. I want to maybe ignore the 5. I'm going to look at this and think, okay, can I group part of the 5? I guess I'm not ignoring it, but the 5 numerically doesn't matter. If it's a 5 or a 10 or 1,000, I proceed the same way. Can I borrow a value to go with the x squared plus 4x to make this factorable? If I group 4 with it, if I do x squared plus 4x plus 4 and group that together, then this factors in a nice way. X plus 2 squared, right? So I've completed the square. How did I know that 4 would do this? Well, the numbers are small enough that I just kind of thought, well, I know that half of 4 is going to be 2. Okay, I'm thinking backwards. I'm thinking about factoring, right? Half of 4 is 2. That's how I go from here to here. And then squaring 2 gives me 4. So whatever this coefficient is, you take half of it and square it. And that's what you need to borrow. So if I had something like, if I had x squared plus 6x plus 10, right? Then pause the video and think about what would I need to borrow to group with the x squared plus 6x so it factors in an easy way. I would need to borrow, well, take half of 6, which is 3, and square it, and you get 9. So I need to borrow 9 so that I can factor, okay? Hopefully that jogs your memory enough with completing the square. So I've got this new version here. And I can say, okay, well, that means over here, I've got the integral of 1 over x plus 2 squared plus 1. And this kind of has the right format, but I do need to do a substitution because I need to get u in this position. So I'll say u equals x plus 2. So du equals dx, which is convenient. So this equals the integral of 1 over u squared plus 1 du. Oh, well, that's going to be tangent inverse of u plus c, which then I can put my substitution back in, put u back in. This is tangent inverse of x plus 2 plus c. Okay, so this is really using some Cal 1 and the beginning of Cal 2, I suppose, although I typically cover substitution in Cal 1. So Cal 2, there's an overlap, right? So far, this is all Cal 1 or the very beginning of Cal 2, right? What if we have something that these techniques don't work for? We have some rational function and neither of these things work. Something like this, and there's a hint on the right. You can see part of it. With this example, the derivative of the denominator is not equal or not proportional to the numerator. So just doing a substitution won't work. And if I try to complete the square in the bottom, I'm going to have an issue because I won't have u squared plus 1. I'll have u squared minus 1. Even if I borrowed appropriately, I'm not going to have tangent here. It's not quite going to work out. So what do? Well, there's something called a partial fraction decomposition. That integrand can be rewritten. If we have 3x plus 11 over x squared minus x minus 6, that can be rewritten, and we'll go into detail later. But I can write that as 4 over x minus 3 minus 1 over x plus 2. Okay, if you take these two fractions, these rational expressions, get a common denominator, and add them up, you get this one. In fact, let's go ahead and do that. Let's confirm that that's true without just assuming that it's true. So on the right-hand side, we can notice that this guy here factors. This is x minus 3 times x plus 2, right? So on the right, if I want to add these together and get a common denominator, this fraction, I need to multiply top and bottom by x plus 2. And this fraction, I need to multiply top and bottom by x minus 3. So, and I'm going to change my stylus to this because otherwise I'm going to run out of room here. So this right-hand side, this equals 4 times x plus 2, right, over x minus 3 times x plus 2 minus 1 times x minus 3, almost said plus 3, over x plus 2 times x minus 3, right? Plus parentheses. So now in the numerators, if I distribute and get 4x plus 8, okay, over, and I could cut corners and just write LCD, but I'll leave it this way, x squared minus x minus 6 minus big fraction x minus 3 x squared minus x minus 6. And now since I have a common denominator, I can add the two numerators together. I guess I really could have done that in one step. 4x plus 8 minus x plus 3. Plus 3 because of the double negative, right? Don't make that mistake. All over x squared minus x minus 6. And if you combine like terms, you get 3x plus 11 all over x squared minus x minus 6. So yes, indeed, this is what's called a partial fraction decomposition, and we've confirmed that this is correct. How do we come up with a decomposition? Well, that we'll address in future examples. I just want this to be an introduction to the technique, and then we'll do several examples in detail. So with that decomposition, what I can do over here is the following. I can say, oh, well, this equals the integral of 4 over x minus 3 minus 1 over x plus 2 dx. And then both of these terms, well, we'll find the antiderivatives individually. And if I want, I could break it into two two integrals and do a substitution, say u equals x minus 3 for the one integral, and then v equals x plus 2 for the other integral, maybe we don't need to bother doing that. It'll work out just like, this one did, right? We'll just have 1 over u is what we'll have. So I'm going to cut corners just a wee bit and observe that this is going to be 4 times ln of the absolute value of x minus 3, right? When you do the substitution here, that's what you get. I'm just cutting corners a little bit. Minus ln of the absolute value of x plus 2 plus c. So if I have a rational function where those techniques don't work up front, maybe there's a decomposition that will allow me to apply those techniques anyway, and I can get around that a little bit. Basically, I'm breaking the larger problem into two smaller problems that are easier to manage. So the rest of this section will basically be, rest of this video, I should say, we'll be doing some variations on this, some other examples, and we'll get into all the details, especially of how do you do this partial fraction decomposition. Okay, so here's our first example of doing a partial fraction decomposition from scratch. I can't, if I try to complete the denominator, complete the square in the denominator, that's not going to work. If I try to just do a straight substitution, that's not going to work. So what I need to do is the following. This rational function, 5x minus 1 over x squared plus x, plus x minus 6. I'm going to take that. I'm going to notice that the bottom factors as x plus 3 times x minus 2. Okay, so this needs to equal something. There's some decomposition where I have x plus 3 in the left term denominator and x minus 2 in the right term denominator. And it's the numerators that we have to figure out, and then we'll have our decomposition, and we can go forward like in the previous example. And it's not that difficult once we get the decomposition, typically. But we'll get to examples where, well, you'll see what I mean. Sometimes there are more steps. This one's our relatively simple example. Now, the numerator is going to have one less degree than the denominator. In this case, since the denominators are linear functions, or linear expressions, the numerators will be constant functions, or constant expressions rather. So two numbers. A might be like 5 and B is -2. I'm making up numbers here. So once we determine what those numbers are, well, then that's it. We're good to go. So what I'm going to do is, I'm going to get rid of this. We don't really need that anymore. What I need to do is take this equation and rearrange it into a polynomial equation rather than a rational equation. There's a couple ways to do this. What I think, to me, makes the most sense, although I am a little short on room, so I'm going to move this. The way that I prefer to write this out, I need more room. In fact, let's just do it here. We have the whole page here, so we have plenty of room. I'm going to multiply both sides by that denominator that we started with. And again, it factors x plus 3, x minus 2. Okay, now on the left, of course, that just cancels. Okay, on the right, when I distribute this into this numerator, I'll end up canceling x plus 3 as a factor. And when I distribute into this term, this numerator, x minus 2 will cancel as a factor. So I'm going to cut corners a little bit, and hopefully everyone's okay with the algebra I'm doing here. On the left, I'll have 5x minus 1. And on the right, I'll have a times x minus 2 plus b times x plus 3. Okay, now ultimately we want a decomposition that is sort of like a trig identity where it's always true, or kind of like if you have x plus y times x minus y equals x squared minus y squared. This is not an equation you would solve. This is simply a fact of algebra, right? The difference of squares always works this way. So when I look at this equation, x is not something you can solve for. This should be true for any value of x at all, any value. Okay, now there's two basic ways to try to solve this for a and b. A and b are the numbers we're looking for, correct? So there's two ways to go. And the method we use just depends on the example. Sometimes one seems easier than the other. Maybe in this example, we'll do both to see how they play out. I'm going to show you the one that I think is usually the easiest. On the right-hand side, I'm going to distribute a. So I get ax minus 2a plus bx plus 3b, okay? Now I'm going to combine like terms, keeping in mind that a and b are numbers. So ax and bx, these are linear terms, right? It's kind of like 5x and 2x, okay? So I'm going to put those together, and I will not worry about saving on space because we should have plenty of space, vertical space. And then the other two I'll put together. So I'll say, okay, minus 2a plus 3b. Okay. Now on the right, I'm going to factor out the x, a plus b times x. And then plus, I'll put this in parentheses. I'll change the order. It doesn't really matter, but I basically want to put the minus in between them. Okay. So 5x minus 1 equals a plus b times x plus 3b minus 2a as a linear equation for any value of x that I want. And that means that this coefficient has to be the same as this coefficient. So a plus b is 5. And this coefficient has to be the same as this coefficient. Because remember, this is as far as x goes, this is an identity equation. This works for any x. So the coefficients have to match. So 5 equals a plus b. And negative 1 rather. Negative 1 equals 3b minus 2a. So I have a system of two equations. I have a pair of equations in the variables a and b, which means I should be able to solve and get a number for a and a number for b. And you can use substitution, you can use elimination, doesn't really matter. I'm going to use elimination in this case. So I'm going to double the the top equation, so that when I add the equations together, a's will cancel. I'll also swap the order of a and b here. So 10 equals 2b plus 2a. And then the other equation is negative 1 equals 3b minus 2a. So when I add these equations together, I get 9 equals 5b. And then I can divide both sides by 5 and get 9 over 5 equals b. I chose this problem kind of randomly. I did not choose one intentionally to have the numbers work out as whole numbers to be easier. I just kind of picked randomly. Now I can take this number, 9/5 for b, and plug this back into, well, I know that a plus b is 5. So a equals 5 minus b, right? Say 9 over 5. So 25 over 5 equals 9 over 5. So 6, minus, which equals 16 over 5. Okay, so there is a. I have a number for a and I have a number for b. Okay, so that means 16 over 5. So that means this is 16 over 5. This is 9 over 5. And that completes the decomposition. If I put those numerators in, then this is an equation that's actually true. So I can copy this guy down here. Say, okay, now we're ready to solve the integral or find the antiderivative. This is the integral of 16 over 5. And I guess I could use decimals if I wanted. That would be 3.2, I believe. Over, was this x plus 3 went first? X plus 3 went first. Make sure you get the order right. Plus 9/5 over x minus 2 dx. And again, if I want, I can separate these into two integrals and do the substitution. U equals x plus 3, v equals x minus 2. Handle them separately, but I feel like I don't need to do that. I know how this is going to play out. So this is 16 over 5 times ln of x plus 3 plus 9 over 5 times ln of x minus 2 plus c. And there we go. That is our antiderivative. So the calculus part really isn't that hard. It's that you have a bunch of algebra, right? And this might be something that you haven't done in a while. So you're going to have to, I don't know, dust off those algebra skills. What I want to do though is also look at another method for solving for A and B. So let's copy this. Oops. Let's copy this and go look at another method, which sometimes we're almost out of space. Okay, hold on a second. I'm gonna make more room. Okay. Okay, now we have more room. So as I said before, this should be true. This equation is true for any value of x. And this approach is not always the easiest, but it is one that we can use. I'm looking at these factors here. Say, well, if x is 2, then this term would be easier. So I could say, well, if x is 2, because remember, this should be true for any values of x that I choose. Well, the left-hand side would be 9, right? Right? If I plug 2 in here, 10 minus 1. This would be 0. And this would be b times 5. And then divide by 5 on both sides. And of course, I get 9/5 b, or for b, right? So same value, obviously. So pause the video. What other x value should I use to find out what a should be? Okay, assuming you paused or you're just waiting for me to tell you, I look at this other factor and say, oh, well, -3 would cause b to go away. So if I put in -3 on both sides, well, here I would get 5 times -3 would be -15 minus 1 is -16. And that equals a times, if I plug -3 in here, I get -5 plus, of course, 0. So -16 equals -5a. And then just divide by -5 on both sides and get 16 over 5a. Equals a, rather. And you might say, wow, that's actually a lot easier. I didn't have to solve a system of equations, which is true. This method does not always work very well. This is the one that is more reliable and will always, always work, although it's sometimes not the efficient way. This one, I think, will not always be the fastest. It depends on the problem. Sometimes it's the quickest. Other times it's not. It just depends. In future examples, I may resort to this, but I will typically use this route in future examples just because it's more reliably, um, yeah, it's more reliable, as I guess what I want to say. That I know how it's going to play out, whereas this method sometimes becomes overly complicated, and it's hard to know at the beginning whether it's going to do that or not when you get started. Okay, let's do another example that works out a little bit differently. So you might notice in this example, the denominator factors as a repeated factor, x plus 2 squared. So I could say that I have x over x plus 2 squared. And it might seem like, okay, well, that means that I want something over x plus 2 plus something else over x plus 2. That would match the example that we just did. Just take the two factors, separate them into two denominators. The numerators are some numbers, and there you go. That actually doesn't quite work. What you have to do is the following. You have to square the second term. Basically, however many you have here, you have to have that many terms here. So if this had been cubed, you would need another one, plus c over x plus 2 cubed. However many, whatever the degree is of the factorization, that's how many terms you have to have. The tops are still just numbers because we have a linear factor. So the numerators over here are 1 degree less than that linear factor, but the denominators kind of go in sequence. We have just linear, we have squared, and we have cubed, because if, and again, that's if this is cubed. If we had to the fourth power on bottom, we'd have 4 terms, and the last one would be x plus 2 to the fourth on bottom, and you have like d on top, for example. But we don't need that many because the denominator that we have in the factorization is just quadratic. It's squared. So this is the situation we have. And once we set that up, we basically proceed the same way. I'm going to multiply both sides by the denominator that we have on the left-hand side of this equation. So on the left, we're just going to get cancellation. And on the right, when I distribute this to this term, I'll just have plus b. The x plus 2 squared on top will cancel with the one on bottom. But the one I distribute over to here, I'll have the x plus 2 squared. One factor will cancel with the x plus 2 on bottom. So I'll have a times x plus 2. So I will get this. X equals a times x plus 2 plus b. Okay? So then I can distribute on the right and get ax plus 2b, 2a plus b. Now the left, I'm going to write as 1x plus 0. Not because I need to, but I want to make the matching of the coefficients more obvious. So then we'll have on the right ax plus, and I'll put this in parentheses, 2a plus b. Okay. So as before, since this is an equation that's true for any value of x, okay, a and b are numbers we'll find, but this has to be true for any x. That means that this coefficient here would have to be the same as this one. So a is 1, and this coefficient here would have to be the same as this one. So 2a plus b is 0. Now, since I just know a number for a, I can plug 1 into the second equation. So 2a, or 2 times 1, plus b equals 0. I can subtract 2 on both sides. B equals -2. Okay. So that means that my integral, and I guess I can just copy paste it down here, this equals the integral of a was 1, so 1 over x plus 2 plus -2 over x plus 2 squared dx. Okay. So notice for both of these, I'm going to use a substitution. Here, I could say u equals x plus 2. And here, I would do the same substitution. So I don't need to break this into two terms as in the previous example, I pointed out, oh, we might have to break this into two terms if we do a substitution. But then I didn't write that out. I just said that u would be this and v would be that, but I didn't go through all the steps. Here, it's the same thing either way. So I can say that u equals x plus 2, so that du equals dx. So I can write this as the integral of 1 over u minus, well, I guess that minus 2 over u squared. Or if I want, I can write this as 2 times u to the -2 power. In fact, let's do that. Du. Okay, so then I get that this is ln of the absolute value of u minus 2 times u to the -1 over -1 plus c. I can simplify a little bit. I get ln of the absolute value of u plus 2 over u plus c, and then I can put x plus 2 back in. So I get ln of the absolute value of x plus 2 over x plus 2 plus c. And there's that example. Okay, so this problem is a little bit different from the previous ones in that the bottom is cubic, so there might be a little more effort in factoring to get started. So I'll start over here, x cubed minus x squared plus x minus 1. And this one's chosen to factor in a relatively easy way. When you have an even number of terms, you can do what's called factoring by grouping. Group the first half and group the second half. Looking at the first half, look for a common factor. Both of these terms have x squared, so I'll factor out x squared. Left over, I'll have x minus 1. And if I distribute this back again, I would have x cubed minus x squared. Looking here, well, there's not really a common factor. I guess I could factor out 1. 1 is always present as a factor, so plus 1 times x minus 1. So now I have a repeated factor. Both terms now have x minus 1 as a factor. So I can factor that out and put the x squared and the 1 together in parentheses. So this is x squared plus 1 times x minus 1. So the first thing I can do is say, well, this equals the integral of 1 over x minus 1. I'm putting the linear term, rather factor first, kind of arbitrarily. It doesn't really matter. I just prefer to put it first. So we factored this, and notice that the this factor does not factor further. All cubic functions over the real numbers will factor as a quadratic times a linear. That will always happen, although it might be ugly. The numbers might not be nice. I've chosen this one so the numbers are easy. But when you have a quadratic, sometimes they don't. Basically, depending on how you count, roughly half of quadratic expressions will not factor with real numbers. They do with complex numbers, but not with real numbers. So this one, there's no way to factor this with real numbers. And we're only using real numbers in Cal 2, so let's not really address the factorization with complex numbers. Anyway, be that as it may, this is good enough. This is all we need. So in order to do the partial fraction decomposition, I'm going to say that I'm going to have 1 over x minus 1 times x squared plus 2. Okay, so I have plus 1 rather. So I have two factors. So the first one will be a over x minus 1. Okay, because the factor on bottom is linear, the numerator must be 1 degree less, it's constant. Plus, since the denominator is going to be quadratic, right, x squared plus 1, the numerator is linear, dx plus c. Okay, it's 1 degree less than the denominator, okay? Or I should say 1 degree less than the factor in the denominator. If this problem were different, and we may have an example like this later, if it were different, and this had been squared, right, then we would also have like a dx plus e over x squared plus 1 squared. We'd have to have another term to make up for this exponent, if that were to happen, right? We don't have that, but if we did, then we would. And I want to point out, that does not mean that the top, since the bottom is degree 4, the top has to be degree 3. No. The numerator has a degree 1 less than the factor it is made for. And if the bottom is squared because you have a square over here, that does not mean that this has a higher degree. It's still linear, okay, dx plus e in this case. Again, we may have an example that's a little bit more complicated later, but these are just our first few. We want to keep it relatively simple. You can imagine if this is complicated enough, you need a bunch of terms, right? Like say if the first one was squared, if this one was actually squared and this one was actually cubed, we would need 5 terms total on the right-hand side over here. Anyway, so standard thing to do is to multiply both sides by the denominator on the left. Okay, on the left, of course, we just get cancellation, right? Real simple. On the right, when I distribute this and it applies to this first term, I'll have a times x minus 1 times x squared plus 1 all over x minus 1. The x minus 1 will go away. In order to save myself a little bit of writing, I'm just going to have a times x plus 1 as a result. When I distribute here, I'm going to have bx plus c in parentheses times x minus 1 times x squared plus 1, but that's all over x squared plus 1. So to save myself some writing, I'm just going to have bx plus c in parentheses times x plus 1. I'm cutting corners a little bit, but hopefully everyone follows that algebra step or algebraic step. Okay. So as before, this is a equation that is true for any value of x. So if I distribute the right-hand side and combine like terms, I'll be able to compare coefficients with the left-hand side. So I'm going to start by doing this. You might say, well, what coefficients? There's just a 1. Well, I'm going to fill in the missing coefficients because I know the right-hand side is going to be quadratic. I'll fill in 0x squared plus 0x plus 1. So I have every term represented. So the coefficients are 0, 0, and 1. okay? And on the right, I'll have ax squared plus a. I'm just distributing. Plus, now I'm foiling, right? So bx squared minus bx plus cx minus c. On the left, I'll just copy what I have. On the right, I'll combine like terms. So I've got two quadratic terms. So I'm going to have a plus b in parentheses times x squared. And then I have two linear terms. So I'll have in parentheses either negative b plus c, then in parentheses times x, or c minus b in parentheses times x. The order doesn't really matter. So plus c minus b times x. And then for my constant terms, I have a and minus c. So I'll put them together in parentheses, a minus c. Okay, so as I said before, this coefficient here will have to equal this coefficient because again, this equation, as far as x is concerned as a variable, is always true for any x, and that means the coefficients have to match. So 0 is a plus b, 0 is c minus b, and 1 is a minus c. So I'm building a system of equations. I get a plus b equals 0. C minus b equals 0, and a minus c equals 1. And we have three equations with three variables, which means we should be able to solve it. There are exceptions, but most of the time they'll be able to. I don't think on any homework assignment or test you'll have to worry about this not being solvable. It should always work. So there's a couple of approaches. I'm basically going to do elimination. I notice if I take the first two equations and add them together, right? If I take a plus b equals 0 and c minus b equals 0, and add those two equations together, the b's will cancel and I'll get a plus c equals 0. And then I can take these two equations, right, and say a minus c equals 1. Well, a plus c equals 0. If I add those two equations together, I get 2a equals 1. So a equals 1/2, okay? And then I can work backwards to find out what the other ones are, right? And basically, so if I have a plus b equals 0, that means 1/2 plus b equals 0, which tells me that b equals negative 1/2. Okay, and then c I can get similarly if I take, I guess this one. Okay, c minus negative 1/2 equals 0. And of course, I have a double negative, so this really says c plus 1/2 is equal to 0. So c equals negative 1/2 as well. And there are other methods for doing this. You could use a matrix. You could use row operations. However you want to solve this is fine. I think for these kinds of problems that we're going to have where we have three equations, elimination works just fine, especially with the kinds of numbers that we're going to have. Anyway, so what this means is this integral, which I'll copy down here. Oh, we're going to run out of room. Okay, let me pause real quick and make room. Okay, so this is going to equal the integral, okay, of x minus 1 with a 1/2 on top, right, plus negative 1/2 x minus 1/2 all over x squared plus 1 dx. And so we're going to have to do a bit of manipulation, shuffle symbols around. I think what I'm going to start by doing is factoring 1/2 and putting it out front, because notice every coefficient in the numerator has a 1/2. So I think I'll start by dealing with that. And then also I will factor, let's do it this way. Let's do it in steps. I'm going to factor negative 1/2 out of the numerator here first. So this is the integral of, let's say, 1/2 times 1 over x minus 1 minus 1/2 times x plus 1 on top over x squared plus 1. Oops, sorry, dx. Okay. So then I'll put the 1/2 in front of everything. And I guess I will give myself some more horizontal room while I'm at it. Okay. Now, it might not be obvious what to do. You might notice that in this term, we can't just do a substitution, because if I do something like u equals x squared plus 1, then du would be 2x dx. And I don't have a 2x anywhere. If this 1 wasn't there, then I could do that. So you might have to look at this a little bit and think, okay, what do I do? How do I approach this? Let's say this equals 1/2 times the integral of 1 over x minus 1 minus x over x squared plus 1 minus 1 over x squared plus 1. And this last term has a minus. Both of them do, because I was subtracting that group. So both fractions have a minus in front. And now the way we handle the three of these is a little bit different. This middle one, now we can do a substitution, u equals x squared plus 1. That'll work fine. This one we can do the substitution, say v equals x minus 1. That'll work fine, but we're going to have to break this into separate integrals. This one you might recognize. Oh, this is just tangent inverse. We don't even need a substitution. So that's what I'll do. I'll break this into 3 different integrals. And the first one we really don't need we don't need to write the substitution out. This is just going to be ln of x minus 1, or ln of the absolute value of x minus 1. The second one I think we should write out. We could do it without writing it out, but I think it would be better to go ahead and write it out. And then this last one is relatively easy. We don't need a substitution for this one. Okay, so I'm going to say, where do I have room? Not on the left. Let's do this. Let's say v equals x squared plus 1. So dv equals 2x dx. Okay, and that's for this middle term. I need to borrow a 2. Okay. So this is 1/2 times ln absolute value x minus 1. And in fact, let's write this 1 with the marks making more obviously a 1. Minus 1/2 times the integral of 1 over x squared plus 1 times 2x dx minus tangent inverse of x squared, of x rather, of x. And I don't need the plus c yet, because I'm not done finding antiderivatives. I'll do the plus c when the last integral is turned into its antiderivative. So this will be 1/2, which I could distribute now. In fact, I will do that. So 1/2 ln absolute value of x minus 1 minus 1/4 times the integral of 1 over u du minus 1/2 times tangent inverse of x. So this equals 1/2 ln absolute value of x minus 1 minus 1/4 ln absolute value of u minus 1/2 tangent inverse of x plus c. And last step, we need to, I just realized, you might have noticed, I almost always use u, but in this case I did use v. If on an exam you make that mistake, don't worry about it. If you have multiple substitutions and you switch where u and v are, then if you're using both, don't mix them up. If you accidentally start using a different letter and then you forget which one you're doing, but there's only one substitution present, then I'm not going to take off points. That's just a mistake. But do try to avoid it. If you notice it when you're almost done, go back and fix it. So 1/2 ln absolute value x minus 1 minus 1/4 ln of x squared plus 1. In fact, you know what? We don't need absolute value bars here because this is always positive anyway. So let's do this. Right? X squared plus 1 can't be negative anyway. Minus 1/2 tangent inverse of x plus c. And there we go. Quite a few steps, but the one we started with, was kind of complicated. And one of the factors was quadratic, which makes things a little bit more complicated when we go do the decomposition, because the numerator of one of them ends up being linear rather than just a number. And that does complicate things. I doubt I can fit this entire thing. Well, let me zoom out enough. Well, sort of. So there's the entire thing. I have to pinch to hold. But there you go. So this is a lengthy problem. There are a lot of steps. Notice how the algebra is basically the first half or so. And then the calculus part is not that difficult once you get the partial fraction decomposition. So we'll start this example as we had with the others by writing down the integrand on the left-hand side. So y plus 1 squared over y squared plus 1 squared. And you might wonder, well, shouldn't we factor the denominator more? Is that it? Well, y squared plus 1 does not factor, so no, we don't need to factor anymore. This one's already factored for us. So because the bottom only has 2 factors, not 4, like if we were able to factor down to more smaller linear terms, or linear factors rather, well, then we'd have, but we don't. So the first denominator will be y squared plus 1. And then the second factor will be y squared plus 1 parentheses squared. If the original denominator had something like this was cubed instead, then we would need another term, something over y squared plus 1 cubed. And if the denominator had originally been to the 4th power, we need another term. However many we have is whatever that degree is in the denominator that we start with. And all of the numerators in each term would be linear. Okay, we'd have something like ax plus b for all of them. Of course, the letters would be different for subsequent terms. So I'm going to say that, well, a y plus b. So a y plus b for the first one, and then c y plus d for the second one. So I'm going to multiply both sides by the denominator I have on the left. On the left, of course, I'll just get cancellation. Right? On the right, when I distribute to that second term rather, the denominator will just cancel completely. When I distribute to the first term, one of the factors of y squared plus 1 will cancel with the denominator, so I'll still have 1 left over. So I get y plus 1 squared equals a times y plus b times y squared plus 1 plus cy plus d. Okay. Now, as before, this is a polynomial equation, and as far as y is concerned, this is not an equation to be solved. This is an identity. This is just true. Y could be any number. So that means if we distribute and combine like terms, then we can match up the coefficients on either side. So on the left, this foils easily. This is y squared plus 2y plus 1, right? On the right, I'll foil this first term, so a y cubed, okay, plus ay plus b y squared plus b plus cy plus d. On the right, I'm going to combine like terms, so I'll have a y cubed, because that's the only cubic term, plus by squared, that's the only quadratic term, plus a plus c rather times y. A plus c times y, because these are my only two linear terms. And then lastly, I'll have b plus d. Okay, on the left, I don't have a cubic term, so I will represent it as 0y cubed plus 1y squared plus 2y plus 1. So that means that a has to be 0. Okay, so that's easy. That's convenient. I was worried we would get a 4 equation system, but no, just 2 because a is 0 automatically. B is 1, so that's convenient. A plus C is 2. Remember, A is 0, so that just means C is 2. And then B plus D is 1, and B was 1, so that means D is 0. So it works out relatively easily. I get A equals 0, B equals 1, A plus C equals 2, but A is 0, so C equals 2. And then B plus D equals 1, but B is equal to 1, so 1 plus D equals 1, so D equals 0. So that worked out kind of conveniently. This whole term in the numerator doesn't matter, it just goes away. And then this one goes away as well. So when I go to copy this down, this is equal to the integral of b, which was 1, over y squared plus 1 plus cy, so 2y, over y squared plus 1 squared. And you might notice that these are not particularly difficult antiderivatives to do. This one is just tangent inverse of y. This one is not hard because if I do a substitution, like u equals y squared plus 1, well, then dy equals, du equals 2y dy, which we have 2y right here, so that'll be easy. So the rest is kind of routine, not that difficult. I'm going to go ahead and separate this into two integrals because one of them needs a substitution, the other does not. So this will be 1 over y squared plus 1 squared times 2y dy. Go ahead and start the substitution over here. So du equals 2y dy. Looks like a 4, but that's a y, just not the best y ever. So this equals tangent inverse of y plus the integral of u to the negative 2 power du. All right, so this will be tangent inverse of y plus u to the negative 1 over negative 1 plus c. So almost out of room there. So tangent inverse of, I can write that neatly, of y minus, well, I guess 1 over y squared plus 1, right, plus c. There you go. That's that example. So some of the WebWork problems are going to require you to do long division before you can apply a partial fraction decomposition. So I wanted to review how to do that. I want to start with numbers first. Let's say I wanted to do, say, 175 over 13, something like that. And I want to do long division, work out what is that. So I could do 13 into 175, and it's not a radical, it's not a root symbol. Just sometimes when I write the division symbol, it kind of looks like it because there's a little foot, but it's not. So since there are two digits here, I'm going to compare to these two digits. How many times does 13 go into 70? Well, 1 time. So 1, and then I multiply the 1 times the 13 and put it below the 17. So 1 times 13 is 13. And then I subtract. Okay, so I get 4. And then I pull down the 5 to continue. So again, how many times does 13 go into 45? Well, 3 times. So I put 3 up here. And then I multiply 3 and 13 to get 39. And I put it here below the 45. And I subtract, and I get 6. So 6 is the remainder. Unless I want a decimal, I'm done dividing. So I can say that this is 13. This is the quotient here at the top, right? 13 and 6/13. Okay. I can write this as a mixed number, or I can put a plus between them if I want. Typically, like in middle school, you wouldn't do that, but here, let's pretend that you need to put a plus, and you'll see why. I want to move this out of the way so we have plenty of room. So let's do long division here. So I'm going to take the divisor, x squared minus 3x minus 4, and I'm going to divide into x squared plus x plus 1. And how am I going to do that? I'm going to say, well, this has 3 terms. How many times can I subtract into this one without, and I'm eliminating the largest degree term? Just like over here, I'm trying to eliminate the 100 by subtracting enough copies of 13 to get down below as small as I can, basically. I don't want to have, oh, well, I can only subtract 0 of them, so I still have 17. No, I'm going to subtract as many as I can to get rid of that 1 if possible. So over here, I want to subtract 1 copy, okay? Because I'm basically comparing the leading term, the leading term to the leading term. How many times can I subtract it? Well, the coefficients are both 1, so the answer is 1 time. So I put a 1 up here. Okay, this is my quotient so far, at least. Then I multiply this times the entire thing here and write it below that one. So I'll have x squared minus 3x minus 4 below that one. And then I'm going to subtract those 2 polynomials. And I have to be careful that I remember I'm subtracting each pair of terms, x squared minus x squared, x minus negative 3x, and 1 minus negative 4. And if there's a double negative, then I'm really adding. So I get 0 plus 4x plus 5. Now, I don't have any quadratic term here, so I'm done dividing. I can't subtract x squared at all. And I wouldn't focus on just these and ignore this one. That's not how it works. This is the divisor, and if I can only go through 1 time, well, then I'll go through 1 time. So this guy equals 1 plus 4x plus 5 over x squared minus 3x minus 4. Okay, that's the long division step. And now I have something where I can consider the partial fraction decomposition because the degree is small enough. If I try to do it here, it won't work. I have to divide first. Okay, so let's do one more example of division. Basically, I start out the same way as the previous step, x minus 1, divided into x squared plus 3x minus 2, okay? I have 2 terms here, so I'm going to focus on these 2 terms, okay? And in particular, I'm going to focus on this term compared with this term. How many times can I subtract x from x squared? Well, if you think about it, about how division works, it's repeated subtraction, right? 17 divided by 2, doing long division, will involve, well, how many times can I subtract 2 from 17? Well, 8 times, right? Essentially, you're dividing but rounding down while you do it. So essentially, when you're doing long division of polynomials, you take this term and divide by this term, and that will always give you the factor that you want. In this case, x. So put x over this term, okay? And then I'll multiply x times this guy and put it below those 2 terms. I'm comparing 2 terms to 2 terms. So I'll have x squared minus x. And I'm subtracting the 2 polynomials. Okay, so and I have to pay attention and watch out for double negatives and negations. So I have 0 plus 4x because of the double negative, and then I can pull down the minus 2. So now I'm trying to fill in this spot, and I have 2 terms comparing to these 2 terms. And in particular, I'm comparing this leading term to this leading term. And I guess even more in particular, I'm going to divide this term by this term because I want to ask how many times can this term go into that one? Well, 4 times. Okay, I'm just dividing them. So I put the 4 up here, plus 4. Then I multiply the 4 against this guy and put it here. So 4x minus 4. and then I'm subtracting the two polynomials, again, watching out for double negatives. So 0 plus 2, because I have negative 2 minus 4, so plus 4 really. This is my remainder. So this equals x plus 4 plus 2 over x minus 1. So if you wanted to do the integral of this guy, you need to do the long division first, and then the antiderivative here, easy substitution. It's not that difficult if you're lucky, and if the denominator is a linear, it's not, there's not quadratic, it's not a repeat factor, then you just need to do some long division. It's not that hard. Okay, in this example, I want to do another partial fraction decomposition that's a little bit more complicated. We won't do a whole antiderivative, just because I don't want this example to be too long, but we'll work through how do you do the decomposition. So looking at this denominator, I've got a repeated linear factor, right? So 2x minus 1 is there twice, and I've got a non-repeated quadratic factor, and this quadratic does not it's irreducible. You can't factor this. You can't break it down into two linear factors. So I'm going to basically, in the decomposition, it's going to go like this. Well, I guess I'll rewrite it here. Let's do this. This example is going to take a lot of steps. So I'm going to write quite a bit smaller so we can fit everything in. And so this should work out space-wise. So I'm going to need one term for 2x minus 1 and another term for 2x minus 1 squared. Okay, and then another term for x squared plus x plus 1. Okay. And the first term, the numerator will just be some number because the degree is one less than the factor that it corresponds to. The next term at the top will be just some number because, again, the degree is one less than the factor it corresponds to. And then the last one will have a linear, so cx plus d, okay? And we'll proceed as we have been by multiplying both sides by the denominator on the left-hand side. Okay, so that, and I will cut corners a little bit, save myself a little bit of time. Just do that. Okay. So of course on the left, well, let's look at the whole thing, right? I'm just multiplying the same thing on both sides. Of course on the left, we just get cancellation. So all that cancels all that, and so the left will just have x minus 1. And then on the right, when I distribute this to each term, when we go to the last term, the quadratic factor will cancel out completely. So I'll have a cx plus d in parentheses times 2x minus 1 squared. And I might FOIL that as I write it down. We'll see. And then when I multiply here, the two linear factors will go away. So I'll have b times the quadratic, x squared plus x plus 1. And then here, just one of the linear factors will cancel. So I'll have a times 2x minus 1 times x squared plus x plus 1. So quite a few. I wanted to do one that was going to be more complicated than the ones we have done already. So here I'm going to have a times 2x minus 1 times x squared plus x plus 1. Then I'll have plus b times x squared plus x plus 1. Okay. And then I will have plus, in parentheses, cx plus d times 2x minus 1 squared. I guess I'll write that as 4x squared minus 4x plus 1. Okay, just to save myself a little bit of writing. Okay, and the left is just x minus 1. So now I have a lot of distribution and or foiling, if you want to refer to it that way. Basically, we'll start here. I'll do 2x times each one of these terms, not factors, terms. And then negative 1 times each one of these terms. Okay, so I will a times 2x cubed plus 2x squared plus 2x, and then minus x squared minus x minus 1. Okay. And then I'll have b times each one of these terms. And, well, I'll leave it to the next step. I'll just, you'll see what I mean. We'll leave this as it is for now. That's fine. And then here, I will distribute this. So cx times each one of these, and then d times each one of those. Okay, so plus, so cx times 4x squared, so 4cx cubed. Okay, minus 4cx squared plus cx. Just checking for errors as I go along. I don't see any. That should be good. Okay, so now distribute the d. So plus 4dx squared minus 4dx plus d. Okay. And of course, the left is just x minus 1. Okay, so now I'm going to distribute a. Well, you know what I'll do next? I'll combine like terms before I distribute. That's fine. Yeah, let's do that. So 2x cubed plus x squared, because I have two quadratic terms, plus x minus 1. Okay, and then here I don't have any like terms to combine, so b times x squared plus x plus 1. And here, I sort of do have like terms, but let's not deal with that just yet. You'll see what I mean in a moment, in the next line. So 4cx cubed minus 4cx squared plus cx. I'm going to double check that. While I'm writing it, I'm going to double check that that's correct by comparing it up here again. So 4cx cubed minus 4cx squared plus cx. Okay. Plus 4dx squared minus 4dx plus d. Okay. Should be correct. Okay. So now, on the left, of course, I still have x minus 1. So now, I'll distribute out a and b to the respective terms. So x minus 1 equals a, so 2a x cubed plus ax squared plus ax minus a. Okay. Plus bx squared plus bx plus b. And then these I'm just copying. So plus 4cx cubed minus 4cx squared plus cx plus 4dx squared minus 4dx d. Okay, so that should be, and we should have plenty of vertical room, I think. So that should be it. That is our polynomial equation. And x, as far as x is concerned, this is not an equation to be solved. This is just an equation. It's an identity for the variable x. So any x value should work and plug in and be fine. So what we're going to do next is on the right, we're going to combine like terms according to the x as a variable. So I'm going to highlight all of the cubic terms first. So these two are cubic. Okay, we'll color code them, and then we'll do quadratic. And make sure to include minus signs if there are any. The negation is always part of the coefficient, so linear terms. And then constant terms. Okay, so I put all the orange ones together, then the green, then the blue, then the purple. Okay, so x minus 1 equals, well, 2ax cubed plus 4cx cubed. Okay, Yep, there's only 2 of those. Okay, now quadratic, so plus ax squared plus bx squared minus 4cx squared plus 4dx squared. Okay. So now linear, the blue one, so plus ax plus bx plus cx minus 4dx. Okay. And then the purple, so minus a. Sorry, can't write the letter A. There we go. Plus B. Can't write B either. Plus D. What I'm going to do is I'm going to go back and put my highlighting back just to make sure I don't have any mistakes. So these are the orange ones. 2ax cubed plus 4cx cubed, okay? And then the green ones should be these 4. ax squared, bx squared, minus 4cx squared plus 4dx squared. And then blue, be these. So ax plus bx plus cx minus 4dx. And then purple, these last guys, minus a plus b plus d. Okay, so that should all be correct. So now what I'm going to do is I'm going to, in each group, factor out that power of x. So I'm going to put 2a plus 4c times x cubed. So the coefficient on the cubic term is 2a plus 4c plus a plus b minus 4c plus 4d times x squared. Okay. Plus a plus b. And at this point, you might be getting nervous. I don't think any test problem will ever be this complicated. Some of the WebWork problems might be. That's why I'm doing one, to show you here's how to do it. But don't worry about tests. I don't think we'll put any this tedious on an exam just because of the time involved. So plus c minus 40. I'll tell you, I've never put one this complicated on a test just because of the time. Plus negative a plus b plus d. Okay. And of course, this is all equal to x minus 1. Now on the left, I want to represent every term with a coefficient. So negative 1 would be the constant term. 1 is the linear term. 0 is the quadratic term. And 0 is also the cubic term, right? So since this is, like I said, an identity equation, this means that this is true for any value of x. That means that this coefficient and this coefficient have to be the same, right? In fact, let me change my colors here. Okay, let's do this. This coefficient and this coefficient have to be the same, okay? This coefficient and this coefficient have to be the same. This coefficient and this coefficient have to be the same, and this coefficient and this coefficient have to be the same, okay? So what I get is 4 equations in the variables a, b, c, d. Okay, so 2a plus 4c is 0, for an example. So I'm going to write that down here, 2a, and I'm going to need room. Let me zoom out and check how much space. Okay. Yeah, we got lots of room. So over here, and again, I don't know how long this is going to take. I might have mentioned I don't know how many steps this problem takes. I haven't worked it out to completion already, so I'm not sure. So I'll write here, then I'll move it over if I need it. So 2a plus 4c equals 0. A plus b minus 4c plus 4d equals 0. A plus b plus c minus 4d equals, oh, not 0, 1. 1, And then negative a plus b plus d equals negative 1. Okay? So let's take this back over here. Yeah, that's probably fine. Right there. It's probably good. Okay. So I have a system of 4 equations and 4 variables. And basically we need to solve this system. And how complicated is that going to be? Well, I frankly don't know. Okay, so at this stage of the problem, I think what's going to help see what to do next is to rewrite this in the following way, leaving spaces. This doesn't have any b's in the first equation, so leaving space. So I'll like put plus 0 in the space for b. So 2a plus 0 to hold a place for b plus 4c plus 0 to hold space for d equals 0. And then 1a plus 1b minus 4c plus 4d equals 0. 1a plus 1b plus 1c minus 4d equals 1. And then minus 1a plus 1b plus 0 plus 1d equals negative 1. And my initial thought is to solve this using elimination. Maybe substitution will be better. It's kind of hard to say what's going to be the most efficient way to solve this. One option is just to do row operations on a matrix, which maybe is the simplest. If we rewrite this as what's called an augmented matrix, basically taking these coefficients here and making a matrix out of them, we can then do row operations to solve. So let's do that. I think for this one, that's going to be the most efficient way. So let's say 2, 1, 1, negative 1, 0, 1, 1, 1, 4, negative 4, 1, 0, 0, 4, negative 4, 1, and then 0, 0, 1, negative 1. Okay. Now there's several ways. Basically what we want is we want to have zeros here in the bottom left, and we want to have ones along what's called the main diagonal. And then either for the rest, we'll have some numbers, or we can go forward and get zeros there as well. How far you want to do row operations versus backward substitution is up to you. So I want to get a 1 in this position and zeros below it. And the order in which I do that doesn't really matter. So what I'm going to do, which I think will be the easiest, is to probably just swap the top 2 rows to get a 1 in this position first. I don't have to do it that way, but it's one way to do it. So I'm going to start with that. So my new first row is 1, 1, negative 4, 4, and then, 1. I'm sorry, 0, rather, 0. And then the second row is the old first row. And then the other 2 rows don't change. Okay, so there's my second step. Now what I'm going to do is I'm going to add the bottom row to the third row to cancel out that 1, making it 0. So the first row won't change. 1, 1, negative 4, 4, 0. And you know, while I'm at it, well, no, I'll do it one at a time. This is complicated enough. We don't need to do 2 steps at once. So I'm adding the bottom row to the third row. So I'm going to get 0, 2, 1, negative 3, 0 by adding. And of course, the bottom row does not change. Okay. Now I'm going to add the bottom row to the second row twice. Okay. So I'm going to not change the first row. 1, 1, negative 4, 4, 0. I'm going to double this and add it here to get 0. Double this and add it here to get 2. Double this and add it here to get 4. Double this and add here to get 2. Double this and add it here to get -2. So my new second row is 0, 2, 4, -2. Oops. 2, -2. Okay. How am I doing on horizontal space? I'm out of horizontal space. Okay, we're going to copy this and take it to the next, take it down to like the next row. And I guess I'll put it right there. Okay. So now I'm going to add the top row to the bottom row to get a 0 in this position. So 1, 1, -4, 4, 0, 0, 2, 4, 2, -2. And you might be noticing something that I'm noticing. The second row has all even numbers, so at some point we might divide by 2. If that's convenient, we can do that. 0, 2, 1, -3, 0. So now I'm adding 1 here to get 0, adding 1 here to get 2, adding -4 here to get -4, adding 4 here to get 5, adding 0 here to get -1. I guess I don't have to undo the coloring, it doesn't matter. Okay, so now the first column is done. I've got 1 with zeros below it, okay? You might recall when you're doing row operations, this is called the pivot, and you use the pivot to eliminate the positions below it. The next pivot is is 2, and we can use it to eliminate the positions below it. You might think, oh, we should divide by 2 first to get a 1 there, and then use the 1 to get rid of the 2's below it. You can, that'll work. I'm going to take a slightly different order and just use that 2 to eliminate the 2's below it. And then after I've got zeros in the 2 positions below these 2 guys, then I'll divide the second row by 2. The order in which you do it is optional. I think the way I'm describing it is a little bit easier. So I'm going to subtract the second row into the third row. So 1, 1, -4, 4, 0. 0, 2, 4, 2, -2, 0, 0, -3, -5, 2. Okay. To review this, make sure I'm not making a mistake. This nothing happens. This I get a 0 in the new position. 4 subtracted into 1 makes -3. 2 subtracted into -3 makes -5. -2 subtracted into 0 makes +2. Okay. And then the bottom row doesn't change at this step. Okay, so now I'm going to subtract row 2 into row 4. Zero, 2, 4, 2, -2, 0, 0, -3, -5, 2. So subtract this into 0, nothing happens. Subtract 2 into 2 to get 0. Subtract 4 into -4 to get -8. Subtract 2 into 5 to get 3. Subtract -2 into -1 to get +1, because I as a result, I'm adding 2. Okay, so 0, 0, -8, 3, 1. Okay, we have room for another step. We do. Okay, now I'm going to divide this row by 2. So I get 1, 1, -4, 4, 0, 0, 1, 2, 1, -1, 0, 0, -3, -5, 2, 0, 0, -8, 3, 1. Okay. We're getting close to the end here. I have some options here. I think what I want to do, I want to avoid fractions if I can. I want to avoid fractions as long as is possible. So what I think I'm going to do is I'm going to try the following. I'm going to I'm going to multiply this row by -3, and you'll see why in a moment. I think this will work well. So this row times -3. Okay, so I'm going to cut corners just a wee bit. I'm going to copy this, and then I will erase that row, and then, perform that change. Whoops. Okay, so this is now 9. This is now 15. And this is -6. Okay, so I've performed the change from the previous row. Now I'm going to add, oops, wrong tool. I'm going to add the bottom row into the third row to force a 1 to show up here. Like I said, I may have said earlier, I think I did. The order in which you do these steps is optional. Just do what everything is most efficient. And as long as every row up, well, two things. As long as you don't go in circles and you do something and then undo it and do it again and undo it, of course, that will get you nowhere. As long as you're always doing valid steps and you're not going in circles, then this should work regardless of the route you choose. So I'm going to get 1, 18, -5. Okay. 0, 0, -8, 3, 1. So now what I'm going to do, something we haven't done yet, because we're getting down to the wire here. I'm going to take this row and take 8 times that and add to the bottom row. So I'll multiply these by 8 sort of mentally, add them here, and then that will change just the bottom row. But I'll leave the third row the way it is. I won't rewrite it while I'm doing this. So 1, 1. I mean, I'll rewrite it as is. I won't rewrite it as in multiplying by 8 and then writing that down and then having to change it back. 0, 1, 2, 1, -1. So 0, 0, 1, 18, -5. Okay, so if my spacing's getting a little bit weird here. Oh well. So if I multiply this by 8 and add here, I get 0, of course. That's why we're using the 8. So 0, 0, 0. This times 8, let me grab a calculator. I don't want to have a mistake at this point. 18 times 8, 144 plus 3, 147. Okay. This times 8 will be -40 plus 1 is -39. Okay. So we are getting down to being almost done because what we have at this point is this last row we could rewrite as the equation 147d equals -39. Remember, this position, these coefficients gave you the coefficients for d, right? In each equation. All right, so let's backtrack and check that we see that. These coefficients here gave you these numbers here. Okay, so all throughout, those numbers give you coefficients for d. So now I could say, oh, well, I can have an equation for d. Let's not do that quite yet. Let's proceed from here. This was a pivot. Oops, wrong thing. This was a pivot, then this, then this. Now this is the pivot. We need a 1 where the pivot is. So I'm going to divide that row by 147. And conveniently, let's see, does that divide evenly? 39 over 147. It reduces. It doesn't divide evenly, but it does reduce. Let's do that here, and then we'll work that out. So the top and bottom are both divisible by 3. So it's -13 over, what is that, 49? Okay, so this bottom row becomes, if I just divide by 147. Okay, so I get 1 0 0. Sorry, I'm writing too small. 1 0 0 0 1 1 0 0 -4 2 1 0 4 1 18 1, and then we get 0 -1 -5 and -13/49. Okay. Now we have some options as to what to do next. I could turn these all back into equations with A, B, C, and D, and that would work fine. Yeah, okay. We will continue with row operations. So, I'm going to start by eliminating these if I can, so I avoid using this fraction until it becomes absolutely necessary. So the first thing I'm going to do is I'm going to subtract this row into that row. Okay, so subtract 1 into 1, 2 into -4, 1 into 4. Okay, so I'll get a 1 0 0 0 0 1 0 0 -6 2 1 0 3 1 18 1, and then 1 -1 -5 -13/49. Okay. So now I can use this 1 to eliminate the stuff above it. So I can take the double of this row and subtract it into the row above it. Oh, we're out of room, so let's do this. We got a little bit of room left. That should be enough to finish the problem. Okay, so this will become 0. Oh, and we were doubling and subtracting. Okay, double and subtract. So 0, -35, 9. Okay, and then now I'm going to take 6 times this row and add it to the top row. Okay. So this will become 0, of course. 6 times 18 plus 3 is 111. So we're going to get 0 and then 111. And then, sorry, I had to clean that up a little bit. And then -29, right? 6 times -5 would be -30 plus 1 is -29. Okay, so 0, oops, wrong tool there. 0, -35, 1, 18, 0, 1, 9, -5, -13/49. Okay. So now I want to start getting rid of these numbers. And the problem is I have to start using that -13/49, so it's going to become a little bit messy. So basically, I'm going to take, let's do the top one first. Let's bite the big one and do the hardest one. I'm going to take 111 times that bottom row and subtract into the top row. So essentially, I'm doing -29 minus 111 times -13/49. Oh, not 149, sorry, 49. So that's a bit of a pain. But that's going to be our new number right here. So we're going to have 1 0 0 0 0 1 0 0 0 0 1 0, we're going to have a 0 here as a result. And then the last value that goes here will be this. Okay, so what's 29 times 49? I get a common denominator. So negative 1421 over 49 plus 111 times 13, 1443 over 49. So 1443 minus 1421 is 22 over 49. Okay, so that's the new number in this position up here. And remember that this is the A coefficient, B coefficient, C coefficient, D coefficient. So 1A equals 22 over 49. So I found 1A, or I found A in other words. So I know what that is. Okay, so let me erase all this stuff. We don't really need it anymore. And let's fill in the rest of what hasn't changed. So negative 35, 9, 18, negative 5, 1, and negative 13 for 49. Yeah, this is getting a little sloppy, but that's okay. Okay, what should change next? Well, let's change the negative 35. So I want to take 35 times this row and add it to that row, the second row. So, okay, so I'm going to need 9 plus 35 times negative 13 over 49. Okay, so 9 times 49, that's going to be 441 over 49 minus 35 times 13, 455 over 49. Is that negative 14? Yeah. So negative 14 over 49. So negative 2 over 7. So this becomes 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 18, 1, 22 over 49, negative 2 over 7, negative 5, negative 13 over 49. And I guess we'll leave that there, or I don't need to erase it, I suppose. Just do that, because we got room. I think we'll be okay. We got room. So now I need to take 18 times this bottom row and add it to the, subtract it into the row above it. So I'm going to need negative 5 minus 18 times negative 13 over 49. Okay, so 5 times 49, so 245. So negative 245 over 49 plus, what's 18 times 13? 234 over 49. Is that negative 11? Yeah, negative 11 over 49. Okay, so the final complete matrix will be negative 13 over 49 at the bottom, negative 11 over 49 for the third row, negative 2 over 7 for the second row, and then 22 over 49 for the top row. Yeah, so that means here's A, here's B, here's C, and here is D. Let me clean this up because I actually forgot. I do want to write out the integral. We did a lot of work to get there. It took a while. That's a lot of algebra. Like I said, there will not be a problem that's complicated on a test. Don't worry about that. Homework, maybe. I hope not. But test for sure not. So that means I'm going to have this. I will save myself a little bit of time. Recycle this. So our integral is going to be the following. So A is 22 over 49. B is negative 2 over 7. And then C is negative 11 over 49 times X minus 13 over 49. And there you go. And then those, how you solve them depends. These two should not be very hard at all. Those are simple substitutions. We've done one like this already. This one, we've done somewhat similar. We had to break it into two integrals. So really you have 4 integrals total here, none of which are terribly difficult. But you know, the tedious part was all of that algebra. So this is just the algebra part. Now you're ready to start doing calculus for this problem. So you can see that you can take a pretty complicated rational function, and it takes a lot of algebra to really get started and be able to apply calculus to it. So like I said, tests won't have one this hard. If a test were to have one that looked this hard at the beginning, like if you look at this and you go, oh no, that's gonna be so bad. Well, it's actually gonna have a lot of cancellation. We wouldn't put one on a test that's like this, so don't worry about it.